BGP, the best path selection mechanism, is quite complicated, but it gives us a lot of flexibility in terms of how we can manipulate the traffic. In particular, what we can do is to determine exactly how the traffic leaves our autonomous system. And to some extent, we can also manipulate how the traffic comes back into our system. Let's see the story so far. So what I have here is on Internet 1, I'm advertising a bunch of prefixes. So let's just focus on the prefixes originated by AS100. If I just jump back here to Internet 1, the best way to see the prefixes originated by the router itself or by the autonomous system itself is to use a regular expression, show IP BGP regular expression. And what we do is the caret and $sign. That means there's no AS number in the path while displaying that information. That's exactly what is happening here. The routes we originate inside our AS have no ASPath in it here. It's in nothing there. And that's what this regular expression can do for us. So these are the four prefixes I originate in Autonomous System 100. They are being advertised over eBGP towards R1 and towards Internet 2. And as such, Internet 2 is also re-advertising them, but it prepends its own AS system to the path while advertising them towards R2. So let's just actually see that as well. So if I jump on R1, show IP, BGP regular expression, underscore is the space 100 ending AS number. So these are the four prefixes. And I can see there's only one path from R1 perspective. That's the best path. There's one hop, one AS path length towards those destinations. However, we also receive the same prefixes from Internet 2 on R2 router here. So if I jump to router 2 real quick and do the same thing, show IP BGP regular expression, space 100 ending with this number, I see that there are two next hop values and there are two paths available. One via R1 next hop, and the other is via Internet 2. The best one shows as through a 1, so this is the greater than sign here. All these are chosen as the best. And now why is that? So let's go back, let's step back a little bit and see this algorithm. I just put this maybe together just to see that. So the first thing what we do if there's multiple paths available on the BGP router is we look at the weight, and we've seen that. Typo. Weight. Now the weight is actually identical for all of these. So if that is equal, the next thing the router is going to be testing is prefer the path with the highest local preference. Now local preference here for those prefixes is 100. Now the one learned over eBGP here is not showing the value, but if we look at the closer show IP BGP 100, let's say one of them, we will see that the local preference is 100 in both cases. So this is from R1. This is the next hop R1. This is the peer address, and this is the router ID of the peer. So again, this is next hop. This is the peer address, and this is the router ID of the box. So local preference is 100 in both cases. So this is not gonna be a tiebreaker just yet. So the next thing we check is the router prefers the paths originated by the local router using a network or aggregate command. These are coming from the external eBGP connection, so they are not local to our router. So the second, as the fourth one here, right after that is the preferring the path with the shortest ASPath length. Now it actually answers our question why this path is better than that one. And the reason being is this is just the one ASPath to cross, and there are two paths, ASPaths to cross, the two autonomous systems. So obviously from here to go through our Internet 2 from R2, we need to cross the AS200, then we go to AS100, and according to the algorithm, the shortest path is the winner. Now, before I actually try to manipulate that, maybe that's going to be next video, I want to see one more thing, because now this actually can get really complex. So for example, let's just jump to R4, because R4 is receiving those prefixes from both R1 and R2. It's a route reflector client, so it is receiving the same prefixes and also has two paths. Now, what is going to be the situation on R4? Let's just jump here real quick, maybe reset my terminal and do show IP BGP. Regular expression coming from originated by 100 AS number, and do a show IP BGP. Maybe in particular, let's go for one of those. So it prefers, so what it seems to be receiving, there's two paths, okay, and what is confusing is that because both paths show next to 1111. So what's the story here? Okay, let's take a look. So this one is actually the preferred one, but to actually answer that question, it's better to display this in particular, one prefix in particular, and look at the details of that. So obviously, the first thing we check is the weight, and weight is the same, 0 for all of these. The local preference, next one, is the same. It's not originated by the router itself, it's just received. So the fourth one is ASPath length, which is identical. All right, what's the story here? So we see that the first one that is considered the best here comes from internal. Internal means IBGP, right? And this is the next hub address. This is the peer we received it from, and this is the peer ID. And once we see that, let's just go back here to my little cheat sheet here. So weight is the same. The local preference is the same. It's not originated by the route itself. The ASPath length is 100 and 100. It's the same. So the router prefers the lowest origin type, IGP. This is when we use network statement or algorithm command, and the incomplete EGP is non-existent anymore. Incomplete when we redistribute prefixes into BGP. That's not the case here. And they're identical. They're basically using IGP statements. So then prefer the lowest metric is 0 here. We'll talk about metric at some point as well. Metric is 0. Multi-exit discriminator. Prefer EGP over IBGP paths. They're both IBGP paths. And we go on and on and on. And finally, what the tiebreaker was is actually this thing. This thing is the router ID, and we checked everything to the point where we prefer the lowest router ID. So it gets pretty complex. But obviously this video is about ASPath length. So now there is a way of manipulating the ASPath in order to accomplish a certain goal. In particular, the ASPath prepending mechanism that I'm going to use in the next video is designed to try to influence, because there's no guarantees. This can always be overridden. We try to influence how the traffic comes back to our system, and that's going to be topic of my next video.